In our previous videos, we learned how to conduct a one-sample z-test using directional or one-tailed hypotheses. Now let's see what happens if we keep everything the same, but instead have a non-directional or two-tailed hypothesis. So we'll continue to evaluate the math intervention program and see how it impacts SAT scores. We'll continue with an alpha of 0.05. And we'll keep our mu naught equal to 500. In other words, if the intervention has no effect, the mean for the population of students who might receive the intervention is equal to 500. In essence, if the intervention doesn't work, we expect to see a mean of 500. What we're going to change are our hypotheses. Previously, with directional or one-tailed hypotheses, we expected the intervention students to score higher than 500. We didn't even consider the possibility that they may score lower. Now, we want to reject the null hypothesis whether the intervention has positive or negative effects on students. We want to reject the null whether the mean for that population of students who may receive the intervention is greater than 500 or less than 500. So our alternative hypothesis will be mu1 is not equal to 500. The mean for the population of students who might receive the intervention is not equal to 500. Our null hypothesis is therefore mu1 is equal to 500. The mean for the population of students who might receive the intervention is equal to 500. Notice how our language has changed. In my alternative hypothesis, I'm no longer talking about the intervention increasing scores. We're talking about it impacting scores. Impacting scores by either raising them or lowering them. We'll keep everything else the same. Sigma remains 100. We'll keep the sample size of 64 and a sample mean of 530. That way, it will be easier to see the impact of switching to a two-tailed versus one-tailed hypothesis. Our standard error of the mean stays exactly the same. It's still 12.5 because our sample size is still 64. How spread out the expected means would be is not impacted at all by whether we're looking at a one- or two-tailed hypothesis. Previously, with a one-tailed test, our region of rejection was completely on one side. We only wanted to reject the null if the intervention led to higher scores. So, based on our alpha of 0.05, we picked a critical z-score of 1.64 because 5% of the distribution of means were equal to or greater than a z-score of 1.64. Only 5% of the time would we randomly end up with a sample whose mean translated to a z of 1.64 or more. That doesn't work now. We want to reject the null hypothesis if our results are sufficiently extreme in either tail of the distribution. But we still need to stick with our alpha level of 0.05. As a result, we can't just keep our old critical z-score of 1.64. We chose it because it would lead us to make a type 1 error 5% of the time in one tail of our distribution. But if we make a type 1 error 5% of the time in this tail and 5% of the time in that tail, we're going to make a type 1 error 10% of the time. What we need to do is split our alpha level in half and put half in each of the tails. That way, we'll make a type 1 error 2.5% of the time in this tail and 2.5% of the time in that tail. So for a two-tailed test, we have two regions of rejection, one in each tail. Based on an alpha of 0.05, we have a new critical z-score for each tail that is based on 2.5% of the scores in that tail being as extreme or more extreme than the critical score. It turns out that that value is z equals plus and minus 1.96. 2.5% of the distribution is above a z-score of positive 1.96, and 2.5% of the distribution is below a z-score of negative 1.96. So assuming alpha is 0.05, for one-tailed tests, your critical z-score is z equals 1.64. And for two-tailed tests, your critical z-score is z equals 1.96. Now for one-tailed tests, when it comes to your calculations, you may plug in either a positive or negative 1.64, depending on which tail your region of rejection lies in. But for two-tailed tests, you always need to remember both tails, so you'll need to plug in both a positive and negative 1.96 into your equations. You can see that right here. Because we have a critical score in each tail, we need to modify the critical z formula slightly and replace our plus critical z times the standard error with plus or minus the critical z times the standard error. A little quick math and we see that the critical scores, the mean SAT scores we need to reject the null, is now 524.5 and 475.5. In other words, we reject the null if our sample mean is greater than 524.5 or less than 475.5. Remember, with a one-tailed test and an n of 64, our critical score was 520.5. It's now increased to 524.5 because we've split that region of rejection in two and moved half of it into the other tail. So relative to our previous one-tailed hypothesis, this does make it a little harder to reject the null hypothesis in that upper tail. On the other hand, now we can also reject the null hypothesis if it turns out that our program is actually lowering scores a lot because we have a region of rejection in the lower tail. We couldn't do that if we did a one-tailed test. So how did we do? A sample of 64 students needs a mean greater than 524.5 or less than 475.5 in order to reject the null with a two-tailed hypothesis. In this case, our sample mean of 530 is still clearly in the rejection region, so we can reject the null hypothesis. But notice our sample mean is a little closer to the critical score. Consequently, if you think about it a bit, you can probably imagine that there may be times where you would reject the null hypothesis if you used a one-tailed hypothesis, but you would not reject with a two-tailed hypothesis. Because of that, sometimes you'll see that someone has conducted a study based on a two-tailed hypothesis, and at the end they find out that they can't reject the null hypothesis, but they're really close. So after the fact, they decide to switch to a one-tailed hypothesis, with their alternative hypothesis being that they would see the results in whichever tail it ended up in. But changing your hypothesis after you've looked at the data
is not allowed
in a research study. If you do, you can end up essentially doubling your actual p-value simply by picking whichever tail is the best one each time. Now, what you may find kind of interesting is that we already know that we can reject the null hypothesis, even though we haven't actually calculated our z-statistic yet. That's because you can basically get to the same conclusion in hypothesis testing through different paths. You can determine the critical value and then see if you've actually crossed that line and entered into your region of rejection. Or you can calculate your test statistic and p-value and see if they're less than the alpha level. They're different routes to the same conclusion, but it's all good information in the end. So let's calculate our z-score and p-value and see what happens when we switched from a one-tailed to a two-tailed hypothesis. Our formula for the z-score is still z equals x bar minus mu naught divided by the standard error of the mean. It hasn't changed. We already saw that our standard error did not change. As a result, if mu naught and the standard mean do not change, our z-score is the same. It's still 2.40. Whether we have a one or two-tailed hypothesis doesn't change our z-score. What has changed is our p-value. Remember, the p-value is based on the probability of obtaining a result as extreme or more extreme than what was observed. With a two-tailed hypothesis, we have to factor in both tails, as extreme or more extreme in either of the tails. Our p-value is equal to the area for a z-score of positive 2.40 or more, or a mean SAT score of 530 or more, which is equal to 0.0082 or 0.82%, plus the area for a z-score of negative 2.40 or less, or a mean SAT score of 470 or less. Because the normal curve is symmetric, this is also equal to 0.0082 or 0.82%. We have to add these two together to get our p-value, which is 0.0164. That's the two-tailed p-value. For two-tailed tests, notice that we basically just double the p-value. That's because we'd reject the null hypothesis whether the result was sufficiently extreme in either of the two tails. So the p-value has to reflect that. So if you're calculating the p-value for a two-tailed test, you can always just calculate a one-tailed p-value based on whichever tail you ended up in, and then double it. So, wrapping up our summary of the problem, we can now say that our z-score was still equal to 2.40, but now this corresponds to a p-value of 0.0164, which is larger but still less than our alpha level, and so we are still able to reject the null hypothesis. Again, nothing has changed other than we switched to a two-tailed test. Our z-score remained the same, but the p-value doubled to reflect our willingness to reject the null in either tail. So that concludes this video, and we're almost done with the one-sample z-test. In our final video of this series, we'll discuss confidence intervals and how to calculate one for our estimated mean. Bye for now.